In this video, we will discuss the concept of ambiguity in context-free languages. In general, ambiguity refers to the fact that the language will give us the possibility to interpret one input in different ways. Let us consider this context-free grammar. E produces E plus E, or E multiply E, or E between parentheses, or N. Here N represents any number N. So it's clear that we will generate with this grammar arithmetic expressions with the operators plus and multiply. Any arithmetic expression may be written between parentheses, and the operands will be in the form of n, which is here a terminal representing any number n. Now let's see how to generate the string n plus n star n. E will be substituted to E plus E according to the first rule. Then this E will lead to a number n. Then the second E capital here will yield to E multiply E according to this rule. And this non-terminal E will yield to a number n. And the last E here will yield to n. And then the string is found in the leaves of the parse tree, n plus n multiply n. Also, we may draw another parse tree for the same string. If we will apply the first rule here, E yields to E multiply E according to this rule, we will obtain these three new nodes from the first symbol E, E multiply E. This E may yield to E plus E, and each E here will yield to N. And hence we will obtain the string n plus n multiply n in the leaves of the parse tree. We obtain two different derivations for the same string n plus n multiply n. So we can say that this string is ambiguous. Why ambiguous? Because it may be generated using different ways. Since there exists such a string that is ambiguous, we will say that the grammar also is ambiguous. Now, since the grammar is ambiguous, can we say that the language of the grammar is ambiguous? Is the language which is composed of all the strings that are generated by this grammar ambiguous? Before answering this question of whether the language is ambiguous or not, let's try to find another grammar which is not ambiguous and which generates the same language. In order to find this grammar, let us recall that we want to generate this type of strings. It may be n plus n multiply n, or n plus n plus n. It may also be any sequence of additions and multiplications between numbers. So we are all familiar with this kind of arithmetical expressions, and we know that when there is a multiplication and an addition in the same expression, we will perform the multiplication operation before the addition. So n multiply n here will be performed first, so the star has a higher precedence over the operator plus. So we may say that any expression will be seen as an addition between multiple terms. And these terms may be just one number or a multiplication between numbers. These are the terms, for example, in this string. So we may say here that any string can be decomposed in a collection of terms. Between these terms, there will be additions. And in the terms, we will regroup the operations of the multiplication. In this case, the precedence of the star operator will be greater than the precedence of the plus operators here. So in this case, we will have 5 terms, and each term is either a number n or a multiplication between two numbers, one multiplication or more than that. And each term may also be seen as one factor or a multiplication between two factors. This factor will be useful for a number if it's just a number like this one. So if we are writing an addition of numbers between parentheses, we need to give higher priority to this operation. So we can use the factor here to say that we have a factor multiplied by a factor multiplied by a factor, and factors will be a number n or an expression e between parentheses. We may see this n plus n here between parentheses like an expression e between parentheses, and this e will lead to many additions between different terms. In this case, we can write the grammar as follows. The new grammar will have 3 non-terminal symbols, E, T, F, and the symbol E will lead to E plus T, which will generate T plus T plus T. And any T here is a term that will be a multiplication between factors. So we'll write T multiply F using the left recursion here to generate a string in the form F multiply F multiply F. And a factor will be any expression between parentheses or a number. We may here check that this grammar G1 generates the same language as the grammar before. So we'll say that G1 is equivalent to G. And for G1, it's not ambiguous. We can check for the same string, for example, that we can draw only one parse tree for this string. Every string is generated in just one way. So to sum up here, we have a grammar G that is ambiguous, but we found another grammar G1 which is equivalent to G and which is not ambiguous. So we say here that the language of the grammar G is not ambiguous, since there is a grammar that is not ambiguous that may generate this language. Now let's give all the definitions related to the ambiguity concept. We will say that a string is ambiguous if it can be generated in 2 or more ways. We can draw 2 or more parse trees for the same string. A grammar is ambiguous if it generates some ambiguous string. So if we find a string that is ambiguous, we will say that the grammar is ambiguous. Now we will say that the language is ambiguous if we don't have any grammar that is not ambiguous that may generate the language. So in this case, we will say that the language is inherently ambiguous. Let's now discuss some examples of ambiguous grammars. For the first example here, we have S is substituted by S concatenated to S, or S between parentheses, or epsilon. So for this example of string left, right, left, right, left, right parentheses, we may think that as we have here a left recursivity and a right recursivity in the same non-terminal symbol S, this may in general lead to ambiguity. We will think about this and try to find a string that is ambiguous. For example here, left right parenthesis, left right and left right parenthesis again. we may think of this double S that may lead to triple S. As you may see here in the first parse tree, we may apply the first rule. S is substituted by SS, and here we'll take the left S here and we will substitute it by SS again. So we will obtain the string SSS, and we will show how to obtain this string from these three non-terminals written contiguously, SSS. The same SSS here may be obtained differently. We may write S is substituted by SS, and then take this right S and substitute it again by SS. So we'll find the same string of non-terminals here, SSS, but in a different way from the first three. Now in the two cases, we'll take each S and change it by S between parentheses according to this rule, and the S in the middle will be changed by epsilon, and we will obtain the string left, right, and left, right parentheses. Same here, each S will lead to S between parentheses, and the S in the middle will lead to epsilon. So we can say here that this string is ambiguous, and hence the grammar also is ambiguous. Since we find one string that is ambiguous, we will say that the grammar also is ambiguous. Let's take another example here in which the ambiguity is not clear from the start symbol. We may say here that S will yield to 0A or 1B. So we'll choose 0A if the input is starting with 0, and we will choose 1B if the input is starting with the symbol 1. But you may stay looking when we will apply the productions or the other non-terminals. Here you have A and B. We may look for an ambiguous string. Let's take this string, for example, 001011. So for the 00 here, we may say that we can apply S derives 0A, and then this A will be substituted to 0AA, and hence the 00 here have appeared in the left part here of the leaves of the parse tree. Now for the third symbol here, which is 1, we have here the non-terminal symbol A. We see here that A may be substituted to 1S or 1. So we may apply A is substituted by 1S, or A is substituted by 1. Now here we have SA, the string SA, and here we have just A. Let's see if in the two cases we may generate the rest of the string here, which is the substring 011. It's possible here to apply the rule S is substituted by 0A from here, and this A will be substituted by 1, and this A will be changed by 1, and we will find that this string is generated. Here in the second part, we may apply A derives 0AA according to this rule, and for this A it will be substituted by 1, and the second A will be substituted by 1, and again we will be able to generate the string 001011. So since we have here two parse trees for the same string, we will say that this string is ambiguous, and hence the grammar here is ambiguous. In this last example, let's consider the syntax of an instruction if. we'll say here that an instruction if is represented by the keyword if followed by a condition followed by the keyword then followed by an instruction, or else it may be in the form if condition then instruction else instruction. And for a condition here, to make it simple, it may be one of the two terminals C1 or C2. And for the instruction, it may be one of two terminals I1 or I2, or else it may be an if instruction. In this way, we will allow for the following syntax: if C1, then if C2, then I1, else I2. So here we have two if and one else. According to the syntax, there may be an if instruction without else or an if instruction with else. So it's possible to have here this syntax, but the question here is, to what if refers this else? From the first view here, we can write if instruction will be substituted by if condition then instruction. And then we have a non-terminal symbol here, cond, that will be substituted by C1. Then we will have this instruction that will yield to if instruction. Then again, we will go back to if instruction and choose the second rule here, and we will write, instead of if instruction, if condition, then instruction, else instruction. Then we will have this condition here that will be substituted by C2. Then this instruction will be substituted by I1, and the last instruction here will be substituted by I2. So here is a way to obtain a derivation of the string if C1, then if C2, then I1, else I2. We have another way to generate the string. We may start by applying the second rule, if instruction is substituted by if condition instruction else instruction. And then for this condition, it will yield to C1. Then for this instruction, it will yield to if instruction according to this rule. Then we will go back to if instruction and choose the rule if condition then instruction. Then for this condition, it will be substituted by C2, and then we will have this non-terminal symbol inst that will be substituted by I1, and the last inst here will be substituted by I2. And here we have another way to derivate the string. And given this possibility to obtain one string from two possible derivations, we will say that this grammar is ambiguous. Let's note that this kind of instruction is popular in programming languages. In general, the developers have the possibility to write a nested if in this way, with, of course, a slight modification in the syntax depending on the programming language. Yes, the grammar is ambiguous, but this is not bad here because to make it easier for the developer to write the syntax in this way.